So in this video I'll talk about some variations on acceptance rejection. You could also say that it's some solutions to some problems with acceptance rejection you might run into. And in particular, because this is quite a short video, I won't have time to go into all the details, so you'll have to look at the books for those. But let's get started. So the first problem you might run into is choosing the g of x function, right? So suppose we want to sample from density like this f of x. There's, as far as I know, no obvious solution to choosing g of x here, something that looks a lot like this. And that means we would be rejecting a lot of samples. But what we can do is then suppose that we can create a g of x which is piecewise linear. And what do we mean by that exactly? Well, we will take some point here and connect it to here, and then we'll connect that with a line down here to here, to here, to here, and so on. Right? And then we can see that we actually have a function which matches this f of x quite nicely. Let's just call it g of x. Right? That's one solution. There's of course a little bit more to it, but this means that you are able to quite generally create excellent functions to sample from proposals. And in some cases you can use something called adaptive acceptance rejection, and what that method does is that it iteratively makes this linear approximation better and better, so that in the limit you'll be accepting all of your proposals, right? So what I mean by that is that the probability of accept converges in probability towards 1, right? So that's one solution to one problem. Another problem you could have is choosing a suitable c. Of course, you want it to be as small as possible, so you will be accepting often. And one solution to that is that we'll record this requirement here, and then we'll take inspiration from that to say that, okay, we'll take c of I plus 1 at an iteration I plus 1. We'll choose that as the maximum of ci hat and f of x over g of x, and then we'll iteratively just update this c, and that it can actually be shown that this what we're simulating from then converges to the right distribution. That's called empirical supremum sampling. Okay, so that's two solutions to two problems. Another quite common problem is what if what if evaluating this expression here is slow, it's computationally expensive? Well, there's a solution for that as well, and it's called squeezing. We'll see why in just a second. And what that does is that, well, we have f of x over c times g of x, and we'll come up with some other function which is fast to evaluate, which is strictly smaller. We'll call it k1 of x, and we can also choose to come up with some function which is strictly larger, k2 of x, which is also quick to evaluate. And then instead of checking this requirement, which is expensive, we'll just check this requirement first, and if u is less than that, then it's certain to be less than this expression, which was expensive, right? So in that case, if it's less than K1, we can accept fast. And we could also say, is it greater than K2? Because if it's greater than K2, then it's certainly greater than this expression here. So then we can reject fast. Of course, then in the middle here, we're sort of out of luck, because then we'll have evaluated K1, K2, and then we still have to evaluate this expression here. But hopefully that can be made to be somewhat rare, right? In practicality, we might have that the expression f of x over c times g of x might look something like, I don't know, something like this. And this is based on a real example. So it could easily look like this, like that, right? And then we might, for example, choose something like a piecewise linear function for our K1. This could be our K1. And we might do the same for our K2. K2. And that will be very quick to evaluate, right? We just have to find these functions, right? And that solves quite a large problem for acceptance rejection, the evaluating of this term here. Now, the next thing is not as much a problem that's being solved as it is just an interesting fact, which is also quite important, even though it's not clear in most cases why it's important. That is that we don't actually need to know the normalization constants. So what I mean by that is, if we want to sample from f of x and it's given by something like K1, and it's a different K1, I just like to use in K's for constants, times f star x, we don't need to know this normalization constant. So what I mean is that this can be unknown. So we don't even really need to know the density which we want to simulate. We only need to know it up to a constant. And the same thing is true for our g function. So this also can be unknown. And an example of that, which I'll show in code in just a moment, is suppose that f star of x, so the unnormalized density we wish to sample from, is given by e to the minus x squared times sin squared of 5x plus cos squared of 2x. Well, this is just a nightmare to simulate from, right? To invert, and there will be a lot of math involved. And in fact, we can't even really say that it's a proper density function, because the integral from 0 to infinity, that's the positive possible outcomes, of f star of x would be, well, it would be approximately 0.9, right? So it's not a proper density, but since we don't even need to know the normalizing constant, we can still simulate from it. And I'll show you that in the MATLAB example now. So in this video, we'll be simulating with acceptance rejection from a density without knowing the normalizing constant. We'll clear the memory in the screen. Then we'll define an anonymous or local function. And this density actually integrates to 1.8 from minus infinity to infinity, and it's symmetric around 0. So it integrates to around 0.9 on the positive axis is where we'll be simulating from. I'll create a number line in x and evaluate the density in y1. I'll use the chi-squared distribution with 1 degree of freedom as the proposal. And I'll get a constant of c equal to 4. Then I'll evaluate my proposals and the envelope and the probability of acceptance. I'm just marking it and pressing F9, and I'm just evaluating this to create this plot, so we can see what the distribution looks like and the other functions. So the target density is the blue line, which goes up and then goes down, and yeah, it's a very weird looking distribution function, you could say. The proposal is the red line, but we can see it's clearly below the blue line. So we're scaling it up by a factor of 4, which is probably way too much, but that's irrelevant for our purposes of demonstrating. To get the envelope, which is the yellow line, we can also see the probability of accepting, which is the purple line, is quite low. In practice, you would use something way better, but this is just to demonstrate. Let's see, we'll just be simulating, let's see, 20,000 simulations. And I'll just speak through this code before I run it. So we'll have a counter for attempts to simulate. We'll have a counter for the ones we accept. And it's all inside a while loop. So while we have less than 20,001 random variables were drawn successfully and accepted, then we'll keep going. We'll first draw from a proposal, and then we'll draw a uniform. Then we'll do the acceptance rejection step here. And if it's accepted, then we'll put the value into y, increase I by 1, and then we'll keep going again. But no matter what happens, we'll increase j by 1. So we can keep a track on how many attempts we have. I'll now mark the code, starting with tick, ending with tuck, which is a timer, so we can get a rough idea of how much time this should take. I'm saying rough because there can always be some background processes in the computer starting up or shutting down, so it can vary a little bit. It's running now. So it took 14.2 seconds, that's fine. Now, normally we would say that the acceptance frequency should be 1 over c, but in the case of having an unknown normalizing constant, we won't quite get that. So we had a c of 4, so we should have had an acceptance frequency of 0.25, and this is actually a bit too far away. I mean, when we have 20,000 observations, we should get quite close to this by the law of large numbers. So we should get quite close to 1 over 4. But that's because we're missing the normalizing constant, so that's fine. And now we'll just do a plot of the histogram, and with the density plotted in. Now the density, we can see in the code over here, I multiplied it by 1 over 0.9 to get something close to the actual density. So the normalizing constant should be something very close to 1 over 0.9, and this makes the plot a little bit nicer. And it looks like we were able to simulate from this distribution without actually knowing the normalizing constant.